Ashish Kumar. Ashish is a PhD student at UC Berkeley. In his first part of his career, he was working in navigation, right? And then maybe he thought that problem is not as challenging, so he decided to make navigation not be on wheels, but be with four legs. So then he decided to do quadruped locomotion, and I think their results are impressive in the sim to real transfer that they show. I think a lot of the work in locomotion was based on model based controllers and very precise design of control schemes, whereas deep reinforcement learning techniques hadn't seen their day from simulation to reality. But I think in the last 1 year there has been a flurry, and Ashish's work is among one of the works which is leading that pack. And today Ashish is going to talk about it, so we are super excited to have him. And also let's thank Aviv for making this seminar possible. So Ashish, before I ask you to take it away, people in the audience, if you are able to switch on your video, I recommend you do it. It's always good for the speaker. And hopefully we can make this interactive. And Ashish, take it away. Looking forward to your talk.
Thanks for the introduction, Pulkit. And feel free to interrupt at any point in the talk if you have any questions. Okay, so I'm going to talk about learning to walk via rapid adaptation. And so let me begin this talk with some videos of our algorithm in deployment in the wild. So here there are no cameras on the robot, and it's only from proprioception. So the robot is trying to cross this difficult rocky terrain. The feet get stuck, it struggles a bit, but then it crosses it successfully. Similarly, here it's going down these stairs on a hiking path. So it doesn't know that these stairs exist because it has no camera, but it discovers them through a fall, and then it adapts and then continues walking forward. This is a construction site in front of my house, and you see that there's loose ground on which it is trying to walk. So the ground is constantly changing and deforming, but we see that the robot maintains stability despite that. And this is a vegetation patch, and the surface underneath is uneven, and it's actually sloping sideways. And you see that the robot is able to walk on it without actually toppling to the left. This is my living room, and I just threw a bunch of planks around, and you can see that these planks are unstable, uneven, and they're moving as the robot moves, but the robot is still able to walk over them. So this is another example of our robot walking 4 times faster than the video that I showed earlier. So in this, the operator almost has to slightly run to keep pace with the robot. And all the videos that I've shown up until now.
Ashish, I think there's a comment saying that if we can optimize video sharing.
I got it. 1 second. Let me do that. Optimize for video and okay. Is this better?
Yes, much better.
Okay, should I quickly show the videos again?
Sure.
Okay, yeah, so this is again trying to walk on this. So you can see that the feet get stuck, and then it's trying to actually figure out. So this has no cameras in it, only has to use proprioception. And in this one, so there are these stairs which it does not know about, and it discovers them the moment it falls over it, and then it adapts and then continues walking. And this was the example where the ground is constantly changing and deforming. So this is right in front of my house. And here the ground is actually sloping sideways, and this was that example where it actually does not fall over on the left and continues walking forward. And this is the example of moving an unstable plank. So the planks are moving along with the feet of the robot. And this is the high speed. Okay, so this is 4 times faster than the previous one, and the operator almost has to slightly run to catch up with the robot. Okay, so all the videos that I showed up until now were actually without using any vision. And in this version, we have cameras on the robot. So the bottom right shows the front view depth camera that the robot sees, and the robot has to get out of this room and the next room, and it has to avoid obstacles on its way to its exit. Okay, so during the course of this talk, I'm going to develop 4 versions of the robot. So the first version is going to do the simple thing of just walking in simulation. We're going to start from there and then try to get the robot to the real world via rapid motor adaptation. And then we're going to generalize this policy to walk at different linear and angular velocities that we command. And once we have this set up, we're then going to incrementally add cameras to it. And we're going to give it this capability to avoid obstacles and navigate its way to a goal. Okay, so let's begin with this work which was published at RSS 2021. And let's get to the first problem, the simplest problem, which is to walk in simulation. Now, before we attack this problem, let's first take a look at the walking literature. So legged locomotion has been analyzed in terms of gaits, and this has been inspired from animal walking. So these animals show several different gaits as I've shown on this slide, and we can see that there's the walking gait, and then there's the trot gait where the alternate legs are in sync. There's a high-speed gallop gait on the bottom right, and several other gaits as well. And once this idea of gaits was around, there was interest in computationally defining it. So Hildebrand in 1965 used the footfall patterns to classify different gaits. So in each of these small plots, you see that a dark circle means that the foot is in contact, and an empty circle means that it is not. And the 4 rows correspond to the 4 feet of the animal. And we can classify these different gaits, and then we can also relate them to the speed. So at what speed, what gait an animal is running or walking at. Now, with this, there was interest in trying to synthesize it on real robots. And here is one example of trying to do it. So these are central pattern generators or some periodic functions like sine waves, and we can have each of these control one leg, and the offset between them can potentially define the different gaits or the footfall patterns that you can see. These gaits were also extensively studied by Mark Rabert, who designed controllers to synthesize them on real robot systems, and he's also the founder of Boston Dynamics. There are several leading labs in the world right now who have been studying this problem of legged locomotion. But let's take a look at human movement in the real world. So in the bottom in the bottom 2 videos, we see that a person is trying to cross this boulder, and the footfall patterns don't actually follow any periodic motion or any rhythmic pattern. Similarly, in the top videos, when a baby is trying to walk, the steps that the baby takes is not periodic or does not have a predefined stride length or a footfall pattern, and it's pretty random. And this has been more systematically studied by Karen Adolph, who's a professor at NYU. So she, in one of her papers, defines this term natural locomotion, which is free-form walking, and contrasts it with straight-line walking in labs, which is centered on classifying walking into gaits. So on the left, that is shown. So straight-line walking, where you measure the step length, step width, and then the periodicity, and then you classify walking into one form of gait. But when you let a baby freely walk, this is the path that it actually takes in a room. And this does not follow any periodicity or any regularity assumption. And this is an example of a video from her lab. So here the baby is trying to just walk, and I'm going to play it down into slower motion, and I'm going to count in which direction the steps are taken. So here is a side, another side, and then forward, forward, forward. Then it takes like 3 very small backward steps. So they were not periodic, they were not regular. And we're going to use this ideology of not using pre-programmed gaits as our core principle on which we will build all the 4 robots. Now, with this in mind, let's get back to the problem of learning to walk in simulation. So we're not going to build any priors, and we're going to learn to walk using data or trial and error. So let me explain the architecture that we have here. So
Ashish, just one thing. Do you mind hiding your panel? I think it comes over your slide headings.
Sorry, the panel is over this. You can see my panel.
Yes, yes. So if you can just maybe do more, right? And there's an option, just click on more. And there's like, hide. Yeah, okay.
Oh, I see.
Oh, okay, yeah. Now it's great.
Okay, thanks. Yeah, so let me first explain the walking, this walking setup that we have. So we have this base policy, and the base policy is going to take the base policy is going to take the current state of the robot as input. So these are joint angles and joint velocities, and it is going to predict the target angles. So the base policy is a neural network in our case, and it is attached to a physics simulation engine, and the task is to learn to walk. So it is going to do that using trial and error and using reinforcement learning. But we don't just want to learn to walk in a single fixed setting, but we actually want this base policy to operate in a whole bunch of different settings. So the payload could be different. The center of mass could change because of that payload. There could be friction in the surface. The terrain height could vary locally. And then the motor strength of the robot can also change. There could be some damage and friction in the motors, which can change over time as well. So we want a single policy to actually handle all of these settings. But the important point here is that we don't want this base policy to actually be blind to any of these changes. We want the policy to know what it is dealing with. So we are going to take this huge vector of all these environment parameters, and we're going to compress it into a smaller extrinsic vector. And this vector is going to be fed into the base policy. So the base policy knows something about the environment, and it also knows the current state of the robot. And now it has to predict the target joint angles. And we're going to train this end-to-end using PPO. So we're going to train this with 1.2 billion samples in simulation. And the important point here is that the reward function that we use does not have any artificial clearance constraint or any predefined foot trajectories. So it's only going to minimize the work and ground impact, and that is motivated from biomechanics and the energetics of the robot. And we are going to train it in a natural terrain setup. So we are going to generate that using a fractal terrain generator, and that's the terrain that you see on the right. And this is the only terrain that we are going to train it in simulation. So
are you trying to maximize the velocity while minimizing work and ground impact?
So we're not maxing, we are trying to go as fast as possible up to a fixed velocity. So that velocity is 0.35 meters per second.
Okay.
So there's a maximum speed velocity at which it can go. So the state is a 42-dimensional, and this extrinsic vector is an 8-dimensional vector. Okay, so now we have this nice looking gate that you just saw. So this solves the problem of walking in simulation. So our first version is complete. Now let's get to the second version of the robot. So in the second version of the robot, we are going to try to walk in the real world, and we'll do this with rapid motor adaptation. But let's first try the simplest thing. So we'll first try to just deploy this system that we have in the real world. Now, when we try to do that, the problem that we will encounter is that we don't actually know the extrinsics at any point, because we do not have the mass, friction, motor strength, any of these available. Because in simulation, we could easily access them and compute extrinsics, but this is not going to be possible in the real world. Now, some people call this the simulation to real gap, but the problem is actually slightly deeper, is actually much deeper than that. So even if I could measure all of these, like the friction, the terrain height in my living room, the robot is not going to work in any of the other settings that I showed earlier. So then how do we approach this problem? So instead of trying to get access to the ground truth extrinsics, we are going to try to estimate these extrinsics using the proprioceptive history. And let me give an intuition of what this means. So if I'm walking on a slippery surface, and if I command my leg or my feet to move in a certain direction or a certain distance, they're probably going to move further than I commanded them to. And that is going to contain information that the surface is slippery. Similarly, if this ground is soft, if I'm walking on sand, they're going to sink deeper than I wanted them to. And that information itself will tell me that the ground is soft. So this discrepancy between what was commanded and what actually happened contains signal about these extrinsics. And we're going to use that to estimate these extrinsics online at runtime. And we are continuously going to do that. So we don't assume that the environment is going to stay static once you've estimated it. So we're just going to do it at a very high speed at deployment time. So now how do we get to the system? So so to train the system, the phase 1 is what we had in version 1. So we were trying to walk in simulation, and phase 2 is what we are trying to get to. So the only difference between phase 1 and phase 2 is that in phase 1 we had access to the ground truth extrinsics, and in phase 2 we want to estimate it using an adaptation module. Now we can train phase 2 in simulation itself using supervised learning. So we can actually take phase 2 back in simulation, and we know what the ground truth extrinsics are, and we know the proprioceptive history of the robot in simulation as well. So we can just go from that and then regress to the ground truth in simulation itself. And once we train this, now we are ready for deployment. Now we can take our phase 2 and we can just deploy it. So during deployment, the base policy is running at 100 Hertz, and the adaptation module is only able to run at 10 Hertz on the onboard compute of the robot. And this does not affect our performance. And this asynchronous design was actually critical for seamless real world deployment. So we did not know ahead of time what these frequencies are going to be. But since this environment or the ZT vector is actually changing very infrequently and not very fast, even 10 Hertz is good enough for the robot to not lose performance. And this is what gives us the single policy to work in all of these setups. So all of these results are from that same policy, which was deployed without any modifications or any fine tuning in the real world. And these experiments were spread over 2 weeks, during which the foot contact sensor got damaged. So some of these results are with that damage to one of the foot contact sensors. So are there any questions on the design of RMA?
I presume if your velocity that you set as 0.35, if that was higher, then you would need your online adaptation module to also run faster.
That is true, yes. So in the limit, if the adaptation module is slower and slower, the performance is going to get dropped, and that is relative to how fast the robot is walking or how fast these changes are going to happen as the robot walks.
So do you think is there a fundamental limitation due to compute, onboard compute right now, or is there any other limit? Why is the velocity restricted to 0.35 and not 1 meter per second?
So we're going to add that as well in a later version, but okay. I think but we're going to add that as a later version. But I think the fundamental limit in this case is not compute, because adapting to the payload or friction, I think if you're doing it 10 times a second, so that's 10 Hertz, I think that is fast enough. But I do think the bigger problem is that proprioception is actually a very delayed sensor. So if there was a way to preemptively figure out some of these things, then that would actually make it faster. So proprioception has this, it's a very fast, compared to vision, it's a very fast high frequency and a low dimensional sensor, but it has this problem that it's a delayed sensor. So I think that is a bigger, more fundamental bottleneck than compute itself. But it's the idea is to show that even if so this is just one aspect which is running on the onboard compute, and there are going to be several more algorithms that we layer on top of it, and then these frequencies are not only going to change, but they could also change unpredictably. So they could run at a different frequency at one point in this. So this asynchronous design becomes critical for deployment, even if let's say we could have a slightly better compute. Okay, now let's try to get an intuition of how the adaptation module works. So this is, again, my living room. So I have this plastic sheet covering, and this is, I'm pouring some oil on it just to make it slippery. And now I'm going to ask the robot to cross it. And it has this additional plastic covering on its feet to make it a bit difficult for the robot to cross. Let's see what happens. So we see that the robot slips, but then it continues to walk. I'm going to play it in a slower motion as well. So here the robot starts walking, slips, and then it continues walking. Okay, now let's analyze what is actually happening inside the robot. So we're going to do this with the help of 3 plots. So the top plot is the gate plot. So the dark portions mean that the feet is in contact, and the light means that they're not in contact. And the 4 rows in the first plot correspond to the 4 feet of the robot. We also plot this knee torque of the front right knee of the robot as it walks. And the bottom plot are the two values from the 8-dimensional extrinsics that we plot. So these are the values which changed the most from those 8 values, and we just show them. So let's see this. So we see that when the robot starts slipping, the extrinsics value change, and they start to capture the fact that the robot is in a surface with low friction, and it continues to capture the fact all through the duration of the run. If we look at the gate plot and the torque, we see that we see some changes when it is slipping, but both of them roughly recover to the right to the same original value. But the extrinsics continues to stay in the changed value to capture the fact that it is still in a slippery surface. So this is another example of adaptation. So this is a payload, a 5 kg payload that I throw on the back of the robot, and the robot is supposed to walk. And let me slow this down and focus on the 3 green dots that you see on the robot. So as the payload lands, you see that there's a dip in the robot. The robot continues to walk and tries to slightly get back up, and then continues walking. And we can do the same kind of an analysis for payload as well. So when the payload lands, we see that the extrinsics actually change to capture that there's a different mass on the back of the robot. And once the extrinsics have captured that, we see that before this adaptation, there's some disturbance in the knee torque and the gait footfall pattern, but that gets recovered the moment the adaptation module captures it. Okay, now let's see what happens if we switch off this adaptation module. So let's first, at the top, we have the regular run with an 8 kg payload. So the mass of the robot is around 12 kg. This is an 8 kg payload. Okay, so now what we can do is that we can make a prediction of the extrinsics in the first time step and then freeze it for the rest of the run. So we can freeze the extrinsics and not actually change it during the course of the run of the robot. And we see that this increasingly, this payload, the change in the center of mass makes it difficult for the robot to lift its front feet, and it actually does fall down. We can also try this foam test where the robot has to cross this foam patch. And if we switch off the adaptation module, we see that it does not get enough clearance to actually cross over this part of the foam. We can also compare to the built-in controller that ships with A1. So the task here is to step down this, and now you see, notice the feet of the robot. It's going to step on the edge, and the moment it does that, it gets destabilized and it falls. And RMA is also going to take a step there, but it is going to maintain its stability. The task here is to again get on this plank, and the feet are going to step on the edge, and this is going to destabilize it very drastically. And RMA again steps in the same or similar location, but it maintains its stability. And this is again foam patch, and even in place the robot gets destabilized while trying to walk on this, but RMA is able to cross it. Let's look at some more indoor results. So these are again the planks that I showed earlier. And notice that the planks move with the feet of the robot, and these would throw off some of the classical velocity estimation algorithms which might be running on board. But we see that RMA maintains stability despite these planks moving and the ground being unstable and all. And this is my bed, and now the robot has to cross this memory foam mattress to get on the other side. So the force feedback on the feet of the robot is different than what it should be on a rigid body. And we did a whole bunch of tests indoors to validate that our method works robustly in all of these settings. We also do systematic comparisons of our method with several baselines. So we see that, so we compare with a bunch of metrics, and we have 3 main baselines. I'm not going to get into the details of this comparison because I think I'm running slightly behind, so I'm going to skip this. We also compare to A1 and the RMA version without adaptation, in several indoor controlled settings in repeated trials and measure the success of each of these methods. And we see that RMA outperforms or matches the performance of baseline methods in all of these cases. And this is some ongoing work in collaboration with Kaushal's lab and a student Zongyu. And in this, we are just trying to get this idea of rapid motor adaptation on Cassie, which is a bipedal robot. So this is still ongoing work. Okay, so this completes the second version of our robot, where we're trying to walk in the real world via rapid motor adaptation. Now let's focus on the third version of the robot. So now we want a general policy so that the robot is able to walk with a different linear and angular velocity in the real world. And this, I think, gets back to your question, Pulkit, on walking at different speeds. So the simplest thing we can do is that we go back to simulation and we just retrain the policy to track different speeds. So let's see what happens when we do that and put it in the real world. So on the top row, we have the videos of the robot walking, and in the bottom row, we have the gait plots. Again, the dark is the feet is in contact, the light is that it is not. And we have the 4 feet, which correspond to the 4 rows in the plot. So let's see what happens when it walks at a slow speed of 0.37 meters per second. So the footfall pattern can be classified as a walk gait when it is trying to walk at a slow speed. When it is trying to walk at a higher speed of 1 meter per second, the alternate feet are actually in sync, and this is closer to a trot gait. And at a very high speed, it converges to a bouncing gait which has a flight phase while it is trying to walk. Now, our algorithm knows nothing about gaits. All it is doing is it is looking at the state and then trying to predict the action at 100 Hertz. And our reward function, or the way we train, said nothing about gaits. So then the question is, why is it that we get different gaits at different speeds? And the answer to this is this. And this is going to be the focus of this segment of the presentation. So this was published in Coral 21. And let me get back to the slide that I showed earlier while training the robot. And one important aspect of this was that we were using energetics and minimizing that to get the robot to walk in a smooth, nice fashion, as opposed to having any artificial constraints such as predefined foot trajectory to add smoothness and clearance. And this energy hypothesis is actually a very popular hypothesis in biomechanics. So in animal biomechanics. So there's this paper in 1981 from Hoyt and Taylor, which studies the gait and energetics of locomotion in horses. So on the x-axis, we have the horse walking at different speeds, and each of the 3 curves you see corresponds to a different gait, so a different style of walking. And the y-axis measures the amount of oxygen consumed when the horse is trying to do that. And we see that the horse prefers or converges to the gait which is more energy efficient at each of these different speeds. And we can do the same test for our A1 robot. So on the left, we use an MPC based controller to force the robot to walk with a certain gait, and we can measure how much energy is consumed to move 1 meter. And we get the same plot, and we see that this behavior is actually very similar to what was observed in this 1981 paper. And the stars that I've overlaid are actually what our algorithm discovers. And we see that it discovers the right gait at the right speed, just from energy minimization. Okay, so let's see some more results. So this is trying to trot, which is 1 meters per second through a grass strand. This is a high-speed bouncing gait, and we'll see that the human operator is going to give some abrupt pulls, and then towards the end, it's just going to lift the robot. And I'm going to play this in a slower motion. See how the robot is at a disoriented angle, but recovers from that. And when the operator pulls the robot up, the feet are actually flaying to get back to normal. So it doesn't care about bouncing gait. It doesn't pay attention to it. It's just trying to walk at an energy efficient way without any predefined notions of gait. And we can compress all the 3 gaits that I showed into a single policy and get this one velocity conditioned policy. All we need to do is to specify a velocity, and then it is going to automatically transition in and out of gaits and figure out how to walk.
And the way you're measuring energy consumption is amount of current that goes in, or is
Uh,
it half like the kinetic energy?
so it is through the work that each of the motors is doing. So it is not the current. So for example, if the robot is standing straight, just standing, that is like zero work.
Okay.
Mhm. So we see that each of these transitions in a slower motion when they happen. So from bounce to a trot gate, so on, and again to this. Mhm. Okay. And now when we ask the low speed policy to actually walk on these planks, we see that it doesn't pay attention to gates. It just walks in an unstructured way, whatever it is needed to actually cross this surface. So this completes the third section of the robot, where we are trying to get this general policy which can walk at different linear and angular velocities. And now we'll get to the fourth version of the robot, where so the task of the robot in this is to navigate to a point goal with only onboard sensing and compute. So for this we are going to attach some cameras to the robot, and we are going to build the system.
So Ashish, maybe before we get into this part of the
Mhm.
talk,
Mhm.
so in the first part of the talk, you were talking about this robot walking on various terrains where the velocity was slow,
Mhm.
right? Then on the second and the third part, you talked about changing the velocity, but the terrains were relatively simple,
Mhm.
right? So there seems to be like this middle ground, like there's some part where terrains can be complex and velocities can be high.
Yes. So I think when the terrain is complex and the velocity is high, at some point we reach a limit of how well can we walk, just from the fundamental limits of how fast can we sense and compute. So I think that's maybe getting back to the compute bottleneck. But I think in those situations, the right thing is to actually slow down. So if we get to a difficult setting and we are, let's say the robot is in a high speed bouncing gate and it gets to a slippery surface or an uneven surface, I think the right thing is to slow down. So I think the one of the point of the first part of the talk is to show that we have a backup kind of a walking style which can handle all of these terrains, but then we have these more higher speed gates where we can walk faster if we want to get to a goal faster.
Okay.
Yeah, and that's actually what we are going to combine in the fourth version of this that I'm going to talk about.
Okay.
So in the it's in the fourth version. So let me first define what a point goal task is. So in a point goal task, the goal is specified as a relative goal vector from the starting position. So an example of this is that the robot has to go 200 meters northeast, and this is relative to the starting position, and the robot has to get there while avoiding obstacles on its own. And it also starts off without any prior map of the floor. So it doesn't know where the obstacles are. All it knows is where it has to get to. And this is a very standard task in mobile navigation. And several people have studied this task for in the recent and in the old uh, times. So but there are two things which we think are missing in these solutions. So the first part is that the navigation should be coordinated with locomotion, and this is related to what you were saying, Pulkit. So you want the navigation system to be aware of the locomotion system and adjust accordingly, and I'll get to this in a second. And the second part which is missing is that vision should be coordinated with proprioception. This is for navigation, not just for walking, but also for navigating. And I'll also get to this in a second, what this means. But let me first develop the base system, and that is going to be the focus of this work. So let's first develop the basic system. So we have this walking policy, so the policy is shown on the right, and on the left, you see that it can like turn and walk at different speeds. It can also do both of these simultaneously and go on curves. So we have this general walking policy from the third version of the robot. Now, what we are going to do is that we are going to freeze this walking policy, and we're going to attach cameras on the robot. So there's a depth camera and a tracking camera. So the depth will give the point cloud, and the tracking will tell where the robot is in the global space. And we are going to use this to get a visual planner working. So the visual planner is going to use this depth and tracking to compute an occupancy map as it moves through the environment. So it starts from no map of the environment. And as it moves, it is getting these point clouds, and it uses them to get a top view occupancy map by accumulating the information that it gets as it moves. So it is going to use whatever partial occupancy map it has at any point to generate a distance, to generate a cost map, which will tell how to get to the goal, which will then be used to generate a path to the goal and get velocity commands that is going to be fed into the walking policy. So the velocity command is going to be the linear and angular velocity. And note that this occupancy map is going to be partial and incomplete, and it is going to build up as the robot moves. So the path to the goal that is being computed is going to need to be recomputed online to update its path depending on the new obstacles that the robot has discovered. And we're going to use fast marching method to actually compute a cost and a path to the goal. Okay, let's see this in action. So this is the video of the robot navigating in a cluttered indoor setting. And on the top right, we see the map that is being constructed, and the bottom right is the front view depth camera of the robot. We see that as the robot moves, it is constructing the map, it is avoiding the obstacle from the onboard depth that it has. Okay, so we have this basic navigation system working, but we're still missing these two components. And let me get to the first one first. So we want the navigation to be coordinated with locomotion. So let's understand that with this example. So if a human is trying to walk across this, and if they stumble on these planks, they're going to slow down to make sure that they're operating at a safe speed. And this is what we want the navigation system to do. So we want the navigation system to actually slow down when the walking policy is at the risk of falling. And we're going to do this. So we're going to make a prediction of if the robot is about to fall using proprioception. Now, note that proprioception always has the signal of if the robot is about to fall and if it is unstable, regardless of if it is because of friction or planks or any other difficult setting. So proprioception is a very powerful signal that we have, and that is what we are going to use to predict the likelihood of falling. And that is what the first plot shows at the bottom. And the second plot at the bottom shows how we adjust the safe walking speed depending on if the robot is about to fall. And let me just play this video. See that the robot will slightly slow down when it immediately enters the plank, but then it speeds up when it knows that it's actually relatively stable to walk on these planks. And then it sees an obstacle, avoids it, and then continues walking. Okay, so now let's get to the second aspect of vision being coordinated with proprioception. So even when the ground is flat, there could be obstacles which can be missed by vision. So let's take an example of this glass door. So let's see what happens when we try to run our policy just on this setting with the glass door. So the glass door is not going to get registered in the depth camera, and the visual planner will think that there are no obstacles in front of the robot, and it is constantly going to ask the robot to just walk forward, even though there are no actual obstacles in front, though it is not possible for the robot to walk through this. But the proprioception history knows that we are trying to walk forward, but we are not able to walk forward. And that signal can be used to figure out that there is an obstacle in front of us, and we can use that to plan a path around it. And that's what we're trying to do on the video on the right. So we'll have the robot first enters into a collision, enters into the second collision, and then changes its direction and then continues walking. So the way we implement this is with this safety advisor module. So our visual planner and the walking policy are frozen. And on the bottom left, we have the safety advisor module. So we are going to implement the fall predictor in this, which will take the proprioceptive history, and it is going to generate some speed constraints for the visual planner. So this is a feedback from the walking policy to the visual planner. And we will also have this collision detector, which is going to figure out if the robot is currently in collision, again using proprioception. And it is going to update the occupancy map locally so that the robot can plan a path around it. Let's see some comparisons of our system with and without the proprioceptive feedback.
On the previous slide, Ashish, everything trained end to end like this. The output of the collision detector feeds into the occupancy map.
So the visual planner part is we use the standard. So there's no learning in the visual planner part. But yeah, so in the occupancy map, so the collision detector just predicts if the robot is in collision. So it's a binary prediction task. And if we see a collision, we just update the map right in front of the robot to indicate a collision so that the robot can plan around it.
And is this like a heuristic that you wrote down for detect collisions?
Not a heuristic. So in simulation, we just simulated the walking policy with lots and lots of instances, one where it was in collision and where it wasn't. And then we trained the collision detector to go from the proprioceptive history to this binary prediction of if it is in collision. And similarly for the fall prediction. So we are trying to just predict if the robot will fall in 1 second. So we simulate lots of different velocities and terrains and all of these, and we collect a lot of data on from proprioception. So we just use that proprioceptive history to figure out if the robot is about to fall, and then we accordingly adjust the speed.
Okay.
Okay, now let's compare the system with and without proprioceptive feedback. So let's first play the system which is only vision, and we see that the person suddenly comes in front of the robot. And since it is too close to the depth camera is not going to register it. And it is going to think that there is space to move in front, and it is going to plan that we should go forward still. But if we add the proprioceptive feedback, the fact that we are trying to move and unable to indicates that there is an obstacle and that we should plan a path around it. This is another instance. So here the robot is trying to work with vision and one with proprioception. So with vision, it actually goes slightly up the tree, and the velocity command that the planner is giving leads the policy to get stuck. Now, what the proprioceptive policy does is treat that as an obstacle and then just plans around it and goes a different way. So vision doesn't see anything, and there isn't anything. But since the walking policy is unable to walk through it, it is just going to treat that as an obstacle and just walk around it and continue walking. Okay, so let me show some more deployment videos. So on the right, there's a map that is being constructed. And the moment there's a collision, we update it locally to indicate that collision that's shown on the right. And then the robot plans a path around and then continues to walk. So, okay, here the robot has to walk over these small banks and this. And there's a very slight slowdown because the feet get stuck in the beginning. We put a very small payload, and again, there is a slight slowdown in the speed of the robot. And when trying to get out of this room, the robot is going to get stuck in, not going to see this glass door because the vision doesn't detect it. But after it collides, it's going to plan its path around it and get to the goal. So this is the goal location. This is another example of outdoor deployment. We see that the planner struggles a bit after the obstacle is actually updated, but then continues walking. And the task is to enter the door on the right. Get here and then replan its way around. Okay. So we also did several systematic studies in simulation. So we have so in simulation, we imported realistic floor plans using Matterport 3D and Gibson. So they're the room floor plans that we have there. We imported them into our physics simulation. And we just randomly change things such as the roughness of the terrain, the friction, the payload. And then we do some controlled experiments on what happens if we have proprioception and if we don't have proprioception for two different settings. One in which we want to see how well does the fall predictor do? That is the bottom table, and the top table tells us how does the collision predictor do. So if the collision with and without the collision predictor, how well does the policy do in terms of getting to the goal? So there's a big difference in collision predictor, and that is to be expected. But even with the fall predictor, it makes a difference in how safe the robot is while getting to the goal, and we see like 7 points improvement over the baseline. And we also, to get a sense of how easy or difficult the setup is, we have simpler comparisons as well that I can talk about later, just to get a sense of how difficult this entire benchmark is. So we import like 200 different maps, and we randomly sample 10 goals in each of these maps, and then we compare to the baselines. And we do similar real world tests as well. So we compare the performance of our robot with the proprioceptive feedback from the safety advisor module to the version without the proprioceptive feedback. So we do repeated trials in the real world in controlled settings. And we see that having proprioceptive feedback improves performance over not having proprioceptive feedback. And this finishes the 4th version of our robot. And now our robot can actually walk on these difficult terrains, can navigate to a point goal, and has a relatively closely coupled walking and a navigation policy, and it can autonomously avoid obstacles as well, all from onboard sensing and compute. So I'm going to end this talk with this epilogue slide. So this idea of layered architectures is a very classic idea which has been explored by Valentino Breitenberg in the book Vehicles, and also by Rodney Brooks in his work on robust layered control systems. Both of these were in the 1980s, and we have taken the key design principles from these ideas, and we have combined them with modern deep reinforcement learning to actually create this generation of walking robots that I have presented during the course of this talk. And this has been made possible by our key technical innovation, which is rapid motor adaptation. And we expect it to be useful in more general settings, which are outside that of walking. Thank you, and I'm happy to take any questions.
So let's thank Ashish for the wonderful talk. So
I can't see anyone, so I'm going to.
Yeah, so now we have time for a few questions. So if people have any questions or comments, now is the time.
Yeah. Hi. Thanks for the great talk, Ashish. I guess my question is, so it seems like your most recent work focuses a lot on how proprioception can like augment vision in order to aid navigation. But I'm wondering if you've also thought at all about how, or whether what your perspective is on whether vision can like augment perception to aid just the balancing or locomotion task itself.
So you mean vision can aid proprioception for the task of walking?
Yeah, or whether there are certain classes. For example, I'm thinking of like walking maybe across stairs, and in settings where actually the robot's gait needs to adapt based on maybe some non-local like terrain information. Is that? Yeah, I'd love to hear your thoughts on that.
Yeah, so I actually think using vision for walking is actually quite important. So there are two types of two types of cases. I'm going to stop my screen share because I can't see my pointer for some reason. Okay, I'm going to stay in this one. So there are two cases where, there's a critical case where you absolutely need vision to walk. And then there are some non-critical cases, but you still want to have vision to walk in those cases. So let me start with the critical one. So if there's a gap in the ground, you need vision to figure out that you need to step over it. Because proprioception, it'll be too late before you figure out that there's actually a gap in the ground and then you're going to fall inside it. The other non-critical case is that, let's say you have small obstacles. The way proprioception works is that it walks, it collides, and then it figures out there's something that I need a higher clearance for. And the problem with that is that it damages the motor slightly. So each of these impacts are damaging the motor. So ideally, just to have a smooth deployment where the robot can actually last for much longer, you need to use vision to preemptively figure out where to step and what is the clearance and how to step on it. So that's the aspect of vision which these two, I think it is very important to actually augment proprioception. And I think they are complementary. So things such as friction or slip might not actually always be visible on an onboard camera. For example, the payload or the motor friction and things like these cannot be always captured by cameras. And I think it is proprioception is useful for those. And those are majority of the setups that we have showed. But there are other cases where vision is also important. And I think it's, yeah, I mean, that I agree with you. Like vision has to complement proprioception, even for walking.
Awesome, thanks. But I guess, right, you chose to address the task navigation sort of as an immediate next step instead of that. So was it, what motivated that decision, I guess? Was just
we are also working on the visual walking project. It just happened to be slower than the visual navigation project.
Yeah, that makes sense.
Yeah.
Cool. Any other questions from the audience?
Hi, Ashish. Thanks for the great talk. Could you please comment on the main challenges of applying this approach to bipeds?
So bipeds?
Yeah.
So I think, so we're still in the process to actually do extensive outdoor experimentation to figure out what the challenge is. I would assume that quadrupeds are somewhat more inherently stable compared to bipeds. And that would make this adaptation slightly trickier because it has to be very fast. But if you're using proprioception to figure out about this adaptation, we are limited. We're limited because it needs to slip a certain amount before it figures out that it is inside a slip. So that is going to limit how reactive and how stable it is going to be in our experiments. But that's actually an empirical question. So for that, we'll have to figure out that, let's say we preemptively tell the robot that this is the friction versus it is trying to figure out what is the difference in accuracy to quantitatively get at it. But I think just because it's an inherently unstable system, it's going to be harder, but just because proprioception might be too slow in some cases.
But just in phase 1, where it's only simulation, what do you get when you apply your architecture?
So I showed the gate. So we get the 1 second. So when we apply our architecture as in this, so we start off by a very, so are you talking about how difficult is it to train?
Yeah, in a way.
I think so we get, so the gate that we showed is kind of what we get. So this is the flat walking is relatively close to what we get in simulation, the process that you see that you're seeing on this. And we build on prior work from this lab where they're trying to walk from simulation to real. But the policy that they use is actually a blind policy, so it doesn't know what it's dealing with. So they use domain randomization to actually go from simulation to real. So it's agnostic, it's a robust policy. And we're going to just trying to change that aspect to see if adaptation can work on a bipedal robot as well.
Cool, thank you.
So Ashish, do you see any fundamental limitations of this approach? Like suppose if I wanted to walk really like a dog or a cheetah.
So I think,
or do you think it's just a matter of scaling?
I think it's, so the way we use proprioception is, I think it's so I think we are limited by sensors. So for example, when the cheetah is walking very fast at a very high speed and jumping and bouncing, it is using vision to walk, which we don't have, for example. So I think this approach in itself has limitations, but that is primarily because of the sensors we are using. Like for example, in this architecture that we have of this asynchronous design, we could very well, or we are still trying to add in a visual sensor and then getting it to walk in the real world. So then it's going to be even better than that. And most of our system, except for that navigation planner, is trained end to end. So all of them can continually, in principle, adapt to falls in the real world and changes in the real world. We haven't gotten to that. But the learning signal that we use is actually computable on board. So we just use how fast is the robot walking, if the robot has fallen down, what is the orientation of the robot, and we just compute and the energy, how much torque is being consumed. We compute our reward function from that. So the robot can, each of the components of the robot can actually continue to learn in the real world. And I think it's a matter of sensing as opposed to the architectures that we have defined. So we have focused on the use of proprioception all the way to navigation, just to see how it can complement vision. But I think like Gabriel mentioned, there's this aspect of vision complementing proprioception, which is going to get that. So I don't see any fundamental limit in terms of what this approach can get. There is this other aspect of how much are we planning to build in to get to a very high speed gate, and if that is necessary. That I don't have an answer to, and I'm not entirely philosophically opposed to using it if it is going to solve a set of tasks. The reason we choose this here is because we were trying to get at a more slow speed general locomotion as opposed to a specialized locomotion. But for specialization, it's possible that we need to build in a few things, and that just gives us the reliability that we want. And I think we should totally use that. So that's I think also what we mean by getting at incremental architectures, incrementally building these generation of robots, because now we can go back and change a few things to add another subsystem so that the high level navigation policy can now switch between walking controllers to actually get different behaviors in different settings, and we can transition in and out of those behaviors.
Cool. Well, thanks a lot, Ashish. Thanks for giving a talk.
Yeah, thanks for inviting. This most of the work happened during COVID, so the robot used to be next to my bed.
I see the robot prattle, huh?
Yeah, exactly. Okay. Yeah, thanks for inviting, Pulkit. It was fun giving this.